All right. Section 7.11 deals with predicting the products. We've looked at a lot of reactions in chapter 7 up to this point. We've looked at SN2, E2 reactions, SN1, E1 reactions. We looked at those elimination reactions. We could form a Zaitsev product, a Hoffman product. We can get E and Z alkenes. We can get inversion of configuration. We can get racemic mixtures. And so these are things that we have to take into account when we're predicting products. So I'm just going to read right off the slide. It says that right now it should be clear that a number of factors are going to affect what products will be formed when you react an alkyl halide with a nucleophile and or base. We've got to consider the substrate, the reagent, and solvent. All of those things have to be taken into account. In a lot of the cases that we've looked at, we end up with mixtures. Right here, we have a secondary alkyl halide. Okay, we have a secondary alkyl halide. We have a strong base, right? Hydroxide is a strong base. It's also a good nucleophile. And so we can get some substitution. You see that we get some substitution here. But the substitution on a secondary alkyl halide is never going to be as effective as it is on a primary or a methyl halide. And so the major product that you get when you have a strong base, strong nucleophile with a secondary substrate is actually the elimination products. So we've got two types of beta protons. We've got these beta protons here, which would give us the major product. Then we have these beta protons here, which would give us the minor product, the Hoffman product. There's no E or Z to worry about here with the major product. So again, the elimination products will be the main products. The Zaitsev product will be the major one. And then, yeah, there's our SN2 product, which underwent inversion of configuration. So all things that we have to take into account. What if you had a tertiary alkyl halide like this? This is tert-butyl bromide. You're treating it with a strong base, strong nucleophile. Well, here we only get one product. Why would that be? Now, if you're thinking, well, come on, what about the solvolysis? Solvolysis reactions that we looked at in section 7.9, right, where the first step was the loss of a leaving group, that was when we were in a polar product solvent. This is not a polar product solvent. This is not methanol or ethanol or water, okay? So here we just have a strong base, strong nucleophile, but we're not going to get any kind of SN2 reaction occurring on a tertiary substrate. So the only possible mechanism that could occur here would be an E2 reaction where the methoxide is going to rip off this proton. We make the double bond and we lose the leaving group. And so what did we evaluate? We looked at the reagent and we looked at the substrate. And here there was no solvent for us to even consider. The only thing that could happen here would be an E2 reaction. So what are we doing in essence, right? We're kind of taking a three-step analysis here. They're not all step one. They're step 1, 2, and 3. Anyhow, first we're going to look at the function of the reagent. Is it a strong base? Is it a weak base? Is it a strong nucleophile? Is it a weak nucleophile? Then we're going to look at the substrate. Is it primary, secondary, tertiary? Is it benzylic? Is it allylic? Right. Then we're going to look at the possible regiochemical and stereochemical requirements and make some kind of evaluation there. Well, in terms of bases and nucleophiles, right? How do we know when something is a strong base, strong nucleophile, et cetera, et cetera? Remember that if you have a strong nucleophile, well, that's going to cause the reaction to undergo some kind of SN2 reaction when you have a strong nucleophile, whereas a weak nucleophile is going to promote an SN1 reaction, right? A solvolysis reaction. Well, what are things that are strong nucleophiles? Something like a hydroxide, a methoxide, an alkoxide, right? An ethoxide, right? Those are going to be strong bases, but they're also strong nucleophiles, okay? Other strong nucleophiles are things like iodide, bromide, chloride, sulfide, hydrosulfide, thiolate, hydrosulfide, or hydrogen sulfide rather. So all of those. And then what about elimination? Well, if we have a strong base, okay, something that's a strong base, again, these are strong bases, but we have other strong bases that don't promote substitution, like sodium hydride, Dbn, and Dbu. I'm going to talk about what Dbu and DBN are in the future in a few slides, okay? But then we have things that are weak bases and weak nucleophiles that would just promote a solvolysis reaction, like water, ethanol, and methanol. So it would be a good idea to memorize this table. Now, I'm not demanding that you do it, okay? But I would say it's probably a good idea to memorize it to start with. And then you'll get so familiar with it that you'll just be able to look at a reagent and say, well, you know, chloride, that's a good nucleophile, but it's a weak base, right? It's the conjugate base of a strong acid. So it's not going to be a strong base, but it's a dandy nucleophile, right? So that's the kind of approach that you want to take. All right. There we go. In terms of Dbu and DBN, you see that they were over here, kind of thrown in the side here. Dbu and DBN are compounds that are great bases. They're very powerful bases, but they're really crummy nucleophiles, just like a hydride, sodium hydride, right? Hydride is a good base, but it's a crummy nucleophile. And if you're like, why can't this be a nucleophile? It's so tiny. It's because it's so non-polarizable that it makes a really crappy nucleophile, pardon my language. So Dbu and DBN, look, I'm going to show you their structures once. I'm never going to ask you to regurgitate their structures or draw them out. I would expect you to be able to recognize them if you saw them on a quiz or something, but usually we just use the acronym. So DBN is this 1,5-diazobicyclo-4,3,0 non-5-ene. We usually just call it diazobicyclononene is normally what chemists call it. It's kind of a shorthand for it. And then DBU is diazobicycloundecane. You can read the whole, or undecane, you can read the whole name here. But the idea is this, is that they both have lone pairs on these nitrogens. So they're both basic, and you can see the reaction here where DBN is behaving as a base. It picks up a proton, and you end up with a resonance stabilized conjugate acid. So that's why it's such a dandy or a great base. But you can imagine that it's really hindered because you've got this big ring here and all of this here. So it's a very hindered base, and that's why it's non-nucleophilic. Okay, it makes a horrible nucleophile. Can you imagine this going in and attack that whole giant thing going in and attacking a little electrophilic center? It's not going to happen, but it can pluck off a proton, right? So they make great bases, but terrible nucleophiles, Dbu and DBN. I know I've never used DBN in my life. If I have, I've forgotten, but I've used Dbu many times when I was in graduate school. I did a whole section of research where I was trying some different reactions using Dbu as a solvent sometimes. So anyhow, something kind of cool there. This is figure 7.20. So figure 7.20, I figure that this is one of the most important tables in all of organic chemistry, okay? This is going to help you make decisions as to whether you're getting SN1 or E1 reactions, or, you know, SN2 or E2. So let's go over a strong base, strong nucleophile. That would be things like sodium hydride, okay, Dbu and DBN. Strong base, strong nucleophile, that would be something like an alkoxide or a hydroxide. So methoxide, ethoxide, hydroxide, right? Weak base, so a crummy base, but a strong nucleophile, that would be anything like iodide, bromide, chloride, hydrosulfide, thiolate, if I can squeeze it in here, a thiol, and hydrogen sulfide, H2S. Those are all really good nucleophiles, but they're all pretty crummy bases. And then the weak base, weak nucleophile, well, you know what that is. That's going to be water and an alcohol. So water, ethanol, methanol, anyhow. So there you go. And yeah, so let's say you had a secondary substrate. That's kind of where we started off. I think that was the first thing that we looked at, right? And we said, okay, we had a secondary alkyl bromide. We treated it with sodium hydroxide. Well, what did we get? We got mostly the products of elimination, wherein we had a Hoffman product, we had a Zaitsev product, and then we had the substitution product, which was an SN2 mechanism. So we had inversion of configuration. So I'll refer back to this table. I might not say 7.20, but we're going to use this to make a lot of decisions. So now what we want to do with all of this information in mind, and yes, it's a lot of information, we're going to take a look at each of the four mechanisms one by one, and we're going to look at some specific examples here. So let's say you have an SN2 reaction, right? An SN2 reaction is going to proceed with inversion of configuration if you have a chiral substrate. I'll just write down an example here off the top of my head. Let's say you had, you know, this compound here. So this is R2 bromo butane, If you were to treat that with hydrosulfide, let's say there we go. Okay. Well, this is a crappy base, okay, but it's a really good nucleophile. This is a secondary alkyl halide. We could draw the product of the SN2 reaction, right? We're not going to get elimination because if you go back here, you've got a secondary alkyl halide and you've got hydrosulfide. So you're going to get SN2, and that's going to proceed with inversion of configuration. So the wedge is going to flip to a dash. So I'm going to go like this, and I'm going to end up with a thiol like that. So I start with something that has the R configuration, and I end up with something that has the S configuration like that. What about an E2 reaction? E2 reactions are cool because you have to evaluate beta hydrogens, and sometimes we have more than one beta hydrogen, right? If you use a bulky base like potassium T-butoxide, let's say, okay, in that case, you're going to get the Hoffman product as the major product because it's going to go for that low-hanging fruit, those least hindered protons, which will produce the Hoffman product. If you use a non-bulky base, like let's say ethoxide, if you use ethoxide or methoxide or hydroxide, right, in that case, you're going to get the Zaitsev product as being the major product. Remember the requirement if you're looking at something that has two stereocenters, your alpha and your beta carbon. Remember that the beta hydrogen has to be anti-periplanar to the leaving group. So these are all things we have to take into account. And then in terms of our Zaitsev product, we have to determine, which one's going to predominate. Would it be cis or trans, right? Sometimes. So all things that have to be taken into account with an E2 reaction. For an SN1 reaction, I think it's always handy to draw the carbocation that's produced. Okay, draw the carbocation, the nucleophile attacks, and remember, if you started with a chiral compound, you're still going to end up with R and S, right? You end up with a racemic mixture. Okay, it says here that there's a slight preference for inversion of configuration. It's discussed in our book, the whole concept of ion pairs. I've never asked a student about that on a quiz or an exam yet. I've never seen it on a standardized exam, so I wouldn't stress about it a whole lot. It's just kind of a cool thing that you can take a look at if you want. There you go. So that's an SN1 reaction. And then for an E1 reaction, again, I think it's always handy to draw the carbocation. We can draw the Zaitsev product, the Hoffman product. Remember, the most stable alkene, which is the Zaitsev, it's the golden rule. Okay, it will always be the major product 100% of the time in E1 reactions. No ifs, ands, or buts. And again, if you have, cis or trans, you have to take that into account for your Zaitsev product probably. And you have to evaluate, well, which one would I get, in a higher yield. The next few slides really just go over this problem in the most gory detail ever. Okay, so we're taking this chiral substrate here, and then we're treating it with sodium hydroxide, and it's just asking, like, what would you get? Instead of going through all the slides, which you can read through, they go through in such gory detail that I think it's actually faster for us to just try to find a blank document here and just kind of think about it as a group. So all it's saying is, let's say you were in a quiz or an exam or a standardized exam, or you were just, practicing with a friend or studying by yourself, and you had this alkyl halide and you were to treat it with sodium hydroxide. What the heck is going to happen? Well, let's start by evaluating the substrate. We have a secondary alkyl halide. And another thing, it's got a chiral center, right? So it's chiral. Okay. Well, I've got sodium hydroxide. How would I evaluate hydroxide? Hydroxide is a strong base. Okay, we know that from Gen Chem 2, right? We know it from this class too. It's the conjugate base of water, which is a weak acid, so it's going to be a strong base. Anyhow, it's also a strong nucleophile. So it's both. Well, remember that SN2 reactions, okay, this isn't a tertiary alkyl halide, so it's not going to be an SN1, right? We can cross that off. It's not going to be an E1. We can cross that off. But when we have a secondary alkyl halide, we saw that SN2 reactions actually predominate when we have a methyl or a primary alkyl halide, okay? Whereas when we have a secondary, the major mechanism here is going to be E1 would be the major, and then SN2 would be the minor product. So let's talk about the E2 products first. Where do I find beta protons? If this is my alpha carbon, I've got beta protons here, and I've got beta protons here. Well, if I was to pull off a beta proton on the carbon that I have labeled in green or red, neither of those are stereocenters. So I can end up with a mixture of cis and trans. Well, if I pull off the green proton, there is no cis and trans to even concern myself with. I'll just write it down here. So I'd end up with this, okay? There's no cis or trans. So if you want to write it like this, it's the exact same molecule, okay? But that would be one of the products, okay? This would be my Hoffman product. Hoffman, okay? But when it comes to the green or the red proton, rather, since there's two protons there, right? There's one going back and one going in front, right? Anyhow, that means I can get both cis and trans, right? Because both of those could be anti-periplanar. So that means I would get this. So I end up with that, which is trans, but it's also the E product, okay? And then I can also end up with the Z product, like this. Okay, this is my Z product. So these are the Zaitsev alkenes. Zaitsev. Could anybody tell me which one would be the major? Would it be the E or the Z? And it's not a trick. I'm not trying to fool you or anything. Based off of what we've learned this morning, which one would be? Yeah, absolutely. Thanks, Mackenzie. It's the E. So this would not only be the E, but this would be our major product of the whole dang reaction, right? Because this pathway, E2, is going to predominates, okay? And then the substitution, we haven't even looked at it, but an SN2 is going to cause an inversion of the stereocenter. So the SN2 product would look like this. All I have to do, come on. All I have to do is change my wedge to a dash and put a hydroxyl out there, and that's it. And that's the product from the SN2. All right. So you end up with a mixture of 4 different products. This would be the major product, would be this Zaitsev alkene, where it's E, and that's it. And we just made the decision using table 7.20. I don't know if you have that table in front of you. I have it on my slide in front of me at my table right now. But if you look up secondary alkyl halide, then you look up strong base, strong nucleophile, you see a rectangle kind of like this, and then it's kind of divided, and it says E2 on one side, and this is SN2 on the other. So E2 is going to be the major pathway, and then SN2 will be the minor. All right, there we go. Give me a thumbs up if you follow me on it. If you're just like, yeah, I think I get it. You know, it's going to take practice. Crazy if you were able to solve all these immediately and just be like, I am the master of organic chemistry. Just watch me. Okay, great. Good. As long as you understand the decision-making process, you're going to find that a little bit of practice is going to go a long way, and you'll be able to evaluate, you know, what will be the major and minor product and these kind of questions really quickly. And again, it's not a race or anything like that, but let me go back to where we were. So I was at this section right, come on, right around here. So here it goes through the whole thing in detail. We analyzed the reagent. We analyzed the substrate. We figured out what the SN2 product was. We figured out all of the different products that can result from elimination. And there we go. We figured out what was the major product. So we've done it already. All right. With that in mind, I think these are great problems. I really encourage you to do all the suggested practice problems for this one. And I know you probably will. So I'm probably just preaching to myself here. But, you know, let's take a look at this problem. Imagine you're on a quiz. I mean, just use your knowledge. Okay, we've got a secondary alkyl halide. Okay, we've got chloride. Okay, chloride is a really crappy base, but it's a strong nucleophile, isn't it? So we'll put here strong nucleophile. It's got a negative charge, but it is a weak base. It's a terrible base. Okay, And we're in a polar aprotic solvent. So we're in an aprotic solvent. I'm just going to ask you guys, instead of me looking at the table all the time, based off of figure 7.20, could anybody tell me which mechanism would predominate here? Or what would be the mechanism? Or would it be an SN1, an SN2, an E1, an E2? Absolutely. Absolutely. Yes. If you go over to that figure, you see secondary alkyl halide, you have a weak base, but you've got a strong nucleophile, you're only going to get SN2. All right. If you're thinking about it, so everybody who answered is 100% correct. Okay. You think about it, why would you get E2 reactions occurring if you've got a horrible base? Right? Chloride is the conjugate base of hydrochloric acid. You know how weak that is as a base? That's not going to be ripping off protons. So all you're going to get is SN2. So we could even just scribble down the product. Okay. I have enough carbons. Yep. I mean, if you want to draw mechanisms, you can do that. Chloride, bada boom, bada bing, like that. Nucleophilic attack, loss of leaving group. We end up with our chloride right there. And this is just an SN2 reaction. Nothing to it. If you want to check the stereochemistry, you look at the first one and it's S. You look at the second one and it's R. Anyhow, you can look at that in your own time. Okay. Let's take a look at the next one. Again, you might look at it and be like, oh my goodness, what's going to happen? Let's just take it nice and slow. We got a tertiary alkyl halide. Okay, so no substitution is going to occur in a tertiary, right? We get a strong base, strong nucleophile. So hydroxide is a strong base, and it's also a strong nucleophile. But why would we get a nucleophilic attack on something that's a strong, on a tertiary alkyl halide? Sorry, I'm thinking of too many things at once here. So if I have a tertiary alkyl halide, strong base, strong nucleophile, I'm not going to get any nucleophilic attack. Could anybody tell me what type of mechanism would predominate here? So if I have a strong base, and I'm looking at figure 7.20, if I have a strong base and strong nucleophile, I've got a tertiary alkyl halide. Could anybody tell me what mechanism would? Yes, it would be the E2 only. Right? If you look at that figure, remember, a tertiary is never going to undergo substitution under no circumstances. Okay, unless it's a solvolysis. If it's an SN1, sure, yeah, then it can undergo substitution. But we're not in a polar protic solvent. We're just having sodium hydroxide here. Right? So now I look at the beta protons. I've got beta protons here, and I've got this type of beta proton here in red. If I was to abstract the one in blue, I would end up with this. So I would end up with this alkene. If I abstract the one in red, I would end up with this alkene. There's no cis or trans to even consider. Okay, there's no E and Z product because you get two methyl groups here that are identical. You get two hydrogens here that are identical. So who could tell me which one do you think would be the major product? Remember, this is a non-hindered base. Would it be the red one or the blue one? Which one would predominate if I have an unhindered base? And maybe I could write that down here. I don't know if you guys can see. There we go. Unhindered. Ugh. Come on. Unhindered base. Yeah, absolutely. It's the red one. So this one is going to be the major product, which is the Zaitsev product. Right. And the other one is the Hoffman, and it's the minor product. So minor, and this is the Hoffman. There we go. All right, let's take a look at the last one. We've got a tertiary alkyl halide. There we go. We got a tertiary alkyl halide. We've got a strong base. However, a tertiary, right? Tertiary or T-butoxide, this is a super hindered base. Okay, this is a mega hindered base. Okay, so this is never going to act as a nucleophile. So let me write that down here. Will not act as a nucleophile. It's too hindered. Never acts as a nucleophile. So even if you had like a primary or a secondary alkyl halide, if you treat it with t-butoxide, it's only going to give you elimination. It's just too dang big to do a substitution. So that means we're only going to get elimination here. All right, tertiary alkyl halide, strong base, crappy nucleophile, but either way, we're only going to get E2. All right. So the last one, I didn't even write it down, did I? The last one is just E2, and then this one is only going to give you E2. There's two types of protons. There's these ones in green, and then there's this one in, I'll use blue. There's this one in blue. If I pull off the one in green, I would end up with this, and I'll have to write it down here a little bit since I'm kind of running out of space. I would end up with this. If I pulled off the one in blue, I end up with this. Could anybody tell me which one would be the major? Would it be the green or the blue? If I've got a super hindered base. Yes, there we go. So here, actually the Hoffman product is the major product. Why? Because the base is so hindered. So here, the Hoffman is the major product, and the Zaitsev is actually the minor product. Okay, again, this is your Hoffman product, and this is your, come on, this is your Zaitsev product. All right, and there you have it, folks. Done. And you see how, you know, just watching me solve the problems is kind of helpful. Why is the chlorine going back when it replaces the bromine? Yeah, so somebody's asking a question about the first one. So I'm going to go over here. Where would I find some space? Right here. So if I'm starting with this compound, okay, where I have the bromine, and I'm treating that with sodium chloride, okay, in DMSO. Well, DMSO is a polar aprotic solvent. So this is polar aprotic, which is going to cause SN2 to predominate. Chloride is a weak base, but it's a strong nucleophile. And then we have a secondary substrate. Okay, so we're going to get an SN2 reaction, right? So SN2 is the pathway that's going to predominate. SN2 occurs via backside attack. Backside, I guess backside is all one word. Backside attack. So since the bromine is coming out towards you, the chloride actually attacks from the back face of the molecule and causes the bromine to leave. And then what you end up with is, since the bromide was kicked out from the front and the chloride came in from the back, you get that inversion of configuration. Okay, does that help? So we get inversion of configuration. All right, cool. Yeah, so SN2 always occurs. Where was I here? There was something in here. Why is my iPad acting like that? So Warren, if you go back here, and everybody else, so when you do an SN2, you always get inversion of configuration. When you do an SN1, that is when you end up with a racemic mixture. Okay, you have a chiral carbon, but you still end up with RNS. Okay, which is really annoying. Okay, if you're doing it yourself, you know, if you're actually in the lab doing the work, it's a real pain in the neck. All right, there you go. So question 7.37, I don't know how many parts there are to it. I'm going to look at my book here. Just give me a sec. Oh, there's a bunch of them. There's A through N. So there's quite a few different parts, and that would be a great question to start with. You know, maybe after lecture today, grab yourself a snack and try that problem, you know, and that will really get the kind of, you start to get a flow with, okay, I recognize my substrate, my reagent, and start making decisions about what would be the major product and what would be the minor product and stuff like that. Okay, we have one section left that deals with new chemistry. That's section 7.12, where we talk about other substrates. Don't you love it? What a great title, okay? It's just others, you know, kind of at the end. And what it means by other substrates, if you think about the first part of this chapter all the way through 7.11, every substrate that we looked at was an alkyl halide, right? It always had a chloride, bromide, or an iodide as a leaving group. Well, now we're going to take a look at some different leaving groups, and I mentioned them very briefly when we talked about pKa's and what makes a good leaving group. I said it's the conjugate base of a strong acid. Well, some other really good leaving groups are called sulfonates, okay? So if you have an alkyl sulfonate instead of an alkyl halide, the sulfonate makes a great leaving group. So let's say you have an alkyl group and you have this thing over here. This is called a mesylate. Mesylate is actually kind of a shorthand for methane sulfonyl, right? You have the sulfonyl portion here, or sulfonyl, however you want to pronounce it. Then you have a methyl here. So that's a mesylate, and we abbreviate that MS. So it's a good leaving group, right? So the MS or the OMS, we'll say here OMS minus, okay? And I'm going to come back to this in a second. Then if you have a toluene sulfonyl, the shorthand for that is a tosylate. So you see how it's toluene, and then you have a sulfonyl, and we call that a tosylate. And OTS minus would be the conjugate base of toluene sulfonic acid, which is a strong acid. And then if you have a triflate, so that's where you have a trifluoromethyl attached to your sulfonate. So it's the conjugate base of triflic acid is this. No, not tosylate. I got tosylates on the brain. This is called a triflate. Well, all three of these things, OMS minus, OTS minus, and OTF minus, these are all excellent leaving groups. Okay, excellent leaving groups. All of these, just like what was in other ones. Bromide was a good leaving group. Iodide was a great leaving group, and so is chloride. Same thing. Okay, the mesylate. Okay, so this is called a mesylate. I guess I could just underline it. The mesylate is a good leaving group. What am I doing? There we go. The tosylate is a good leaving group, and the triflate is a good leaving group. Again, they're just everything that I have highlighted here in yellow. These are just the conjugate bases of strong acids. All right. There we go. So the reason why sulfonates are such good leaving groups is, again, they're the conjugate bases of strong acids. And why are they so strong? You know, why would they make strong acids? Because when they lose a proton, you end up with a sulfonate that is resonance stabilized. That's super stable, right? Why is chloride a good leaving group? Because when it's by itself, it's stable, right? So why is tosylate or mesylate or triflate a good leaving group? Because what's left over is stable. The sulfonate is stable, right? If you look at their conjugate acids, you have methane sulfonic acid, toluene sulfonic acid, and check this one out. Are you ready for this? Look at this. Triflic acid. So this is trifluoromethane sulfonic acid. The shorthand name is triflic acid. So this one we sometimes call triflic acid. This one we sometimes call tosic acid. And methane sulfonic acid, I don't think there's a shorthand for that. But anyhow, look at this, a pK of -14. Is it just me, Jerry, or is that a strong acid? That's a strong acid, right? That's a very, very powerful acid. Out of all of these, if I had a choice to use any of them as a leaving group, I would pick this one. The reason why is because tosic acid or toluene sulfonic acid is a solid at room temperature. So you can just weigh it out on a balance. It's really easy to work with. Whereas these ones, they're a little trickier to work with. I don't even know if I've ever used triflic acid for anything in my life. Anyhow, how do you make these alkyl sulfonates? Well, you start out with your alcohol. You treat it with the chloride analog. So let's say you wanted to make a tosylate. You would treat it with the chloride analog of toluene sulfonic acid. So for all of these, you would just replace the hydroxyl on all three of these with the chlorine. And you'd get methane sulfonyl chloride, toluene sulfonyl chloride, and trifluoromethane sulfonyl chloride. Here's my pen. And so you treat it with the chloride, tosyl chloride. It does this substitution reaction. So the first step is that this comes in as a nucleophile, and you lose the leaving group. Then you do a proton transfer using pyridine, and you end up with your tosylate. So now you've made a good leaving group. So if you're wondering, well, I'm tired, what's the point of all this? The point is that every substrate, again, that we've seen up to this point was an alkyl halide. It was just a chloride or a bromide or an iodide. Well, now what we're going to do is we spent a lot of time in chapter 12 talking about what? Alcohols. So now we're going to learn a way to take an alcohol and make it into a good leaving group. Okay, so that we could do substitution or elimination reactions on it. So realize that when you do this, you're just putting the tosyl group on the oxygen. Okay, the reaction is occurring at the oxygen, and so you don't get an inversion of configuration. So if you want to take an alcohol, which is a horrible leaving group, and convert it into a good leaving group, you treat it with tosyl chloride or toluene sulfonyl chloride and pyridine, and bada boom, there you go. And you get retention of configuration, okay? There's no reaction at this carbon. So you get retention of configuration. So if you start it with S, you get S. If you start it with R, you get R. Only after you do a substitution reaction could you change the chirality. So let's say we had a primary tosylate. That's the same thing as if you were to have this. Okay, just a good leaving group. So if you treat that with a strong base, strong nucleophile, what's going to be the major pathway? It's going to be substitution. Okay, and you're going to get a little bit of elimination. Let's say you had a secondary tosylate. It's the same thing as if you had this. What's the major pathway? Elimination. And you get a little bit of substitution. That's it. Okay, so you treat it the same way you would an alkyl halide. So with that in mind, let's get a little practice. It says predict the major and minor products for each of the following reactions. If we were to start out with this alcohol, we've got a chiral center. You see that the alcohol is on a dash, but remember when we treat it with tosyl chloride and pyridine, in the first step, we retain the configuration. Nothing changes. So we still have our dash, but now we have OTS. That's the same thing as if I was to write this. Okay, it's the exact same dang thing. So now I have a secondary leaving group, so it's secondary. I'm treating it with a strong base that is a poor nucleophile. Okay, horrible nucleophile, but a great base. So what's the only thing that's going to happen is elimination, is E2. So I'm going to get an E2 reaction. I've got these beta protons, and I've got these beta protons. If I rip off the one in red, I'm going to end up with this product, okay? And if I rip off the one in green, I'm going to end up with this product. There's no E or Z for either of these, and the major product is going to be the one in red, the Hoffman product. Why? Because this is a hindered base. Hindered base. Okay, there we go. Could anybody tell me what mechanism is going to predominate in the second reaction after I install or convert the alcohol into a leaving group? Could anybody tell me what mechanism would predominate? I've got a primary leaving group. I'm treating it with a strong base, strong nucleophile. Which one would predominate? So if you go over to figure 7.20, you look at primary and you see strong base, strong nucleophile. Yes, absolutely. It's going to be SN2 that would predominate. So the major product would be the SN2. There's no chiral center to worry about. So SN2 would give you this. We have OET. This would be your major product. Major. And then your minor product that don't have a lot of room here. But that would be the E2 product. And there's only one possible E2 product, which would result from the abstraction of this proton. So you end up with this, and that's your minor product. And that's it, my friends. That's how you do it. All right. Let's move on to section 7.12. We're still in the same section, but the last little section deals with alcohols. Okay, still talking about alcohols in ways that we can convert alcohols into or convert them into something that's got a good leaving group, right? What was our strategy in the first part? was to convert them to tosylate, right? Because tosylates are great leaving groups. To make a tosylate, you just take any alcohol, treat it with tosyl chloride and pyridine, bada boom, bada bang. To convert an alcohol into a good leaving group, like a bromide, for example, there are other options, okay? For example, if you take a primary alcohol and you just treat it with hydrobromic acid, you can actually convert it into a primary bromide. Now, how the heck would that work? Well, you need a really strong acid like HBr to do this, because this is a horrible leaving group, right? This is a terrible leaving group. Hydroxide as a leaving group, you never see this in organic chemistry, because hydroxide is the conjugate base of water, which is not a strong acid. So this is a poor leaving group. But if I protonate it with a strong acid like HBr, now I convert it into a good leaving group. And so the bromide can come in and act as a nucleophile. I get my nucleophilic attack and my loss of leaving group occurring, and I make an alkyl bromide. So it's an SN2 reaction. So that is a reaction that you want to have in your bag of tricks, right? Taking a primary alcohol, converting it to a bromide using just HBr. Now, what about a tertiary alcohol? What could I do with that? Well, if I treat that with HBr, you're going to protonate the alcohol, convert it into a good leaving group, which can leave to make a carbocation, and then my nucleophile, my bromide, can come in, do a nucleophilic attack to make a tertiary alkyl halide, which could undergo solvolysis under the right conditions. So again, the reason why you can do this, the reason why this can happen, is because strongly acidic conditions are, by definition, protic conditions. If you have HBr, I mean, that's protic. I mean, it's going to be in water too. There's going to be some water in there. So it is protic conditions, and that's why it can happen. Okay, this is why we can protonate the alcohol, and it can leave, and then we can have an SN1 reaction occurring. There's a typo on here I just noticed. That's not good. It says here, but since primary carbocations are too unstable to form. Oh, no, it's, yeah, okay, it's not a typo. Sorry, I was reading it too fast, trying to do too many things at once. And this is probably my favorite reaction out of all the reactions that we learn in this entire chapter. It's the very last one. Okay, so if you're tired, and I understand, I would totally get it if you were. This is my favorite reaction. Why? Because sulfuric acid is super cheap. Okay, I don't want to spend a lot of money in a lab, and I also don't want to waste a lot of atoms that can go into the environment and pollute. So if you have a tertiary alcohol, okay, and you just treat it with sulfuric acid and you heat it up, what it does is an E1 elimination, and you always end up with the most stable alkene. So doesn't matter, like this one, there's only one possible product, but I'll write it over here. You usually get the Zaitsev product. And so if you want to take an alcohol and you want to get the Zaitsev alkene, all you've got to do is heat it up in acid. That's it. What does the acid do? It protonates the alcohol, converts it into a good leaving group. You lose water to make the carbocation. You're already in protic conditions, so that can happen. And then you get a proton transfer to form the alkene. So again, one of my favorite reactions. I love to use this reaction as much as I can in this class. Later on, we're going to talk about what's called green chemistry, which is not chemistry where the reactions are actually green, but it's chemistry that's good for the environment, right? Where we try to minimize pollution. So with that in mind, let's take a look at this one here. It says predict the major product for each of the following reactions. I want to start with this one. It's my favorite reaction. You have a tertiary alcohol. You have concentrated sulfuric acid and heat. You always get the Zaitsev, okay? You've got beta protons here, and you've got beta protons here. You're going to pull off only the ones in red, okay? After you protonate this, it becomes a good leaving group. It leaves, and you only get this product. You get the Zaitsev product only. So Zaitsev only. Super cool reaction. The next one, let's draw the mechanism just for fun. Remember, the first step is a proton transfer. So I have lone pairs here. I do my proton transfer. I convert that hydroxyl into a good leaving group. Got my positive charge here. The leaving group leaves like that. So I end up with my carbocation. I draw that tertiary carbocation. Now I have my bromide, which can act as a base, or sorry, as a nucleophile rather. Bromide is a horrible base, so acts as a nucleophile. There we go. And we end up doing our overall substitution like that. There's no chirality to worry about. If there was a chiral center, you'd end up with a racemic mixture. Right? Anyhow, there you go. And that's it. And those are two of the reactions that we looked at in the last couple of slides. And then here it asks you to draw a plausible mechanism for each of these transformations. So what I would like you to do before class on Monday morning is to try drawing these two mechanisms for 7.43. And this is where we're going to start on Monday morning. Then we're going to take a look at section 7.13, which shows you all the different types of reactions that we learned with primary halides. And this could also be a tosylate, you know. Then we're going to look at all the reactions that can occur with a tertiary halide. And again, that could be a tosylate as well. And then we just kind of discussed synthetic strategies. Anyhow, there's all kinds of funny things here about a brick house. Again, this is Dr. Klein's words that I just took out of the textbook. You know, he's got all kinds of different ideas. But I think that in this chapter, retrosynthesis can be really handy, you know, in terms of making decisions as to how to make compounds. So we could sit here and discuss retrosynthetic analysis all day. But it's the kind of stuff that you've already covered, or that we've covered all these reactions already. And so when we come back on Monday morning, what we're going to do is take a look at the remaining problems, and then we're going to try a bunch of practice problems. So I encourage you to look at as many practice problems as you can before class on Monday, if not all of them. And if there's a particular one that you would like me to go over in class, I'm more than happy to go over any of the practice problems that I suggested from the problems in the back of the book or the ones in the chapter or whatever. But we'll start here at question 7.43 on Monday.